Okay, so in this video we are going to prove that the closed bounded interval AB is compact. So proof. So it's going to be a proof by contradiction. So our initial step is to suppose the opposite. Suppose it's not compact. Suppose AB is not compact. Then that implies that there exists an open cover, and we will call the sets U for open, alpha being its index, and saying that it's a arbitrary index. It might be uncountable. It's not necessarily countable. Are an open cover U alpha such that AB is contained within the open set U alpha, the union over all of alpha U alpha. So it's contained within the union of all the open sets. And there is no finite subcover. So basically we're just saying that if it's not compact, then there exists an open cover for which there is no finite subcover. Okay, now what we do is we divide up the interval. So we have, in the real line, we have some closed bounded interval AB here. We're going to cut it in half, so we have B plus A over 2. So cut it in half, split it into, we'll call this middle point M1, the first middle point. So split up AB into A to M, M1 rather, union M1 to B. So split it into these two bits. And now, because there was no finite subcover for this, we know that the union of alpha mu U alpha contains AM, and it also contains MB. And basically, for at least one of these, there can exist no finite subcover. There can exist no finite subcover. The reason being that if both of them have finite subcovers, then just union those two finite subcovers together and you'll get a cover of AB, and that will be finite, so it will contradict there being no finite subcover over AB. Okay, so now we can go further. We can say, okay, so that means that over one of these there is no finite subcover, so pick whichever one it is. Of course, it may be the case that for both of them there is no finite subcover, but just pick one of them. It has to be for one of them, so pick one. So pick this interval, and divide it into again. So you get another middle point, M2. So let's say it's this interval. You'll divide this and you'll get M2. And the same argument applies again. So you get another interval in which there can exist no finite subcover. For which this open cover has no finite subcover. So you get a sequence. Of nested intervals. So you have this original interval AB, and then in that contained within that you have this interval I1, which is half the size of it, then I2, and they're all contained within one another, I3. Now there is a theorem from topology which we're going to prove in a moment. Theorem from topology. We're not going to prove it topologically, we're just going to, from topology, that the union of nested intervals is non-empty. We're just going to prove it in the real line. Intervals is non-empty. Sorry, not the union, the intersection. I.e. there is some element, there is some x there is some x which is an element of the real numbers, such that x is an element of in for all n is an element of the natural numbers. Okay, and that we could say is the limit of these. They converge down onto this point x. And now I'm just going to prove this theorem is called the nested interval theorem. Nested interval theorem. So let's try and prove it for the real line. So we want to prove that if we get this sort of continually smaller intervals, there is some point that is common to all of them. Okay, so how are we going to do that? Well, basically we can look at the lower bound for this, the infenum of these. They're all closed intervals. Note, they're all closed bounded intervals. They are all closed bounded intervals. Are all closed bounded intervals. Bounded intervals. And therefore have a maximum and a minimum. They contain their supremum and their infenum. Have a maximum and a minimum. Okay, so in this case A and B are the minimum and the maximum, and in these cases you can see where the maximum and minimum are. Okay, so consider the sequences of the minimums and the sequences of the maximums. Consider the sequence of, let's say, sequence of minimums. Well, it forms a sequence going up. It forms a monotone sequence, a monotonically increasing sequence. And we know that in the real numbers, providing a monotone sequence is bounded, it converges to something. And similarly, we can say that the lower sequence, this maximum sequence, also converges to something. We also use the fact that basically what we can, okay, so I'm going to write some of that down. So if we look at the sequence of minimums, I'm just going to move this up. Minimums. Then we know that it is monotone. It is monotonically increasing. It's not necessarily strictly increasing, because the minimum doesn't necessarily have to get bigger. For instance, if we had the first interval AB and the interval that had satisfied the property, or that there was no finite subcover, was this interval, then the next interval would have the same minimum. So it's not necessarily strictly increasing, but the next term is either equal to the last term or it's bigger than it, so that it is monotonically increasing. Therefore, and also note, it is bounded. It is bounded by B. So all the minimums are bounded by this value here. Therefore, it has a limit. Okay. Similarly, the sequence of maximums. The sequence of maximums has. The sequence of maximums is monotonically decreasing, and is bounded below. By A. Okay. It converges to a limit 2. As well, 2, I think, double O there. Right, so if we put, we let little m of n be the sequence of minimums, and big M of little n be the sequence of maximums, we know that this is always greater than or equal to mn, isn't it? The worst possible scenario is that you get down to an interval, or well, actually we know stronger than that. We know it's always going to be greater than that. So unless you had an interval which was some point x and then x, which contains only the point x, then the minimum would be x and the maximum would be x. But we're halving the interval every time, so we're never going to get down to that. Surely, it's obviously converging on an interval like that, which is the crux of all of this. That's the intuition for why this theorem is true. That it's converging down to an interval like that, which still contains one point at least. But all other intervals, all the intervals that are actually in the sequence, we're not talking about the limit, we're talking about the sequence. Little m of n is going to be less than big M of n. So therefore, the limit as n approaches infinity of little m of n is less than, but we have to add the equal in there. N is equal to infinity mn. How can I explain that? You can have two sequences where one is always bigger than the other, but they still converge on the same limit. The only case that cannot happen is that this one somehow ends up bigger than this one. So it's less than or equal to this. So that means that either case... Okay, I'll get another piece of paper. So two things can happen. Case 1. Limit as n approaches infinity of the minimum values of n is not equal to the limit as n approaches infinity of big M of n. Of course, we know that's not going to happen because the intervals are getting smaller and smaller and smaller. But if this were the case, then this would have a limit here, this would have a limit here. This one would have to be greater than this one, therefore it would converge on this interval, and all of these points would have to be contained within every interval, because all the other intervals, the minimum is less than or equal to this, and the maximum is greater than or equal to this. Therefore, it would have to contain all of this. Hence, job done. Case 2, they're equal to each other, equality, which means that you've got this point in the middle of all the intervals, this point which we'll call x, which is the limit of these two things, and so x is equal to limit as n approaches infinity of little m of n, which is equal to limit as n approaches infinity of big M of n. Okay, so they've converged down onto this thing, and it means that this point must be in absolutely every interval, because any interval you take, the minimum is going to be less than this, and the maximum is going to be greater than or equal to this. Therefore, this interval must contain this point. The worst possible scenario is that you have got one that's equal to it, and another one that's equal to it, and then it still contains that point, basically. So it's quite a simple theorem. It's, in this case anyway, I think it's extended hugely, it's generalized hugely. But in the real numbers, it's quite a simple theorem. That's the nested interval theorem. So, back to our proof. It implies that this sequence of intervals we had, so we started off with AB, we then had that contained within I1, which was contained within I2, these intervals that are halving in length each time, I3, and there is a rigorous notion of length, it's measure theory, I4, and we go on and on and on. It's halving. There exists an x, which is an element of all intervals In, for n is an element of the natural numbers. So the intuitive picture is that we have our original interval AB, we then divide it up, and we take another interval, we divide that up, we divide that up, we divide that up, and there's some point here that's always going to be within absolutely every single one of them. So we were using that interval there. Okay, so what do we now need to prove? Okay, this means, but there must exist an open set in our open cover, containing x. So we'll call this u sub, what should we call it? U sub x. Let's call it u sub x. So u with curly u sub x is the open cover that contains x. So x is an element of u sub x. But we know what the open sets. We know what open sets look like. What open sets look like in the real line. Sets look like in the real line. The real line. They are unions of intervals. They are unions of open intervals. Therefore, u sub x must have an open interval containing x within it. X within it. So take this open interval. So look at this open interval. It may be that ux is a nice open interval that just contains x, but it might be a union of open intervals. The point is that it has this open interval. Look at it. So let's call this open interval u1 to u2, and x is an element of that, and it is a subset. It's a subset of ux, potentially equal to ux. Okay. Okay, so that is where we are at the moment. Okay, but eventually. If I take the length of this open interval, if I take u2 minus u1, that has some number, that has some value. So take u over 2 minus u over take oh no wait okay, so x is somewhere within this open interval. So let's draw a picture. U1 to U2 of x, and x is somewhere in there. We don't know where x is the difficult thing. Now what we want to show effectively, what we're trying to show is that at some point one of these intervals will be solely within this open interval, and then after that all intervals will be in there, and that's a contradiction, because that means that this interval that we had is contained within u1, u2, which is contained within ux, which means that this singleton open set here would cover that interval, which is a contradiction, because these intervals were all supposed to have no finite subcover. So basically all I need to do is show you that that at some point one of these intervals will be fully contained within there. So basically just look at x minus u1 and look at u2 minus x as well, and make an interval such that the length of interval therefore needs take the minimum of these, needs to be less than, therefore length of interval needs to be less than the minimum of these divided by 2. Okay, let me explain why. So x is somewhere within this open interval u1. We want to stick our interval in here, and it's going to sit around x. But we don't know where x is going to sit in that interval, so you have to make sure that when you, if we make a bigger picture, u1, u2, x is anywhere within here, but there is a distance, and this would be the minimum in this case. So we want to take the minimum of the distance between here and here, and we want to find an interval that is solely within there. So we need the length of this interval to be less than the minimum of these, otherwise it's not going to sit within there, is it? There's a chance that it might not sit within there. If it is less than the minimum of this distance here, which is this, and this distance here, which is this, divided by 2, then we're in with a chance. Oh well, it just has to be less than whichever one. The length of it just has to be less than. Why did I get the 2? All because the x point could be right at the end here, so I could have this interval like position there and the x would be there. So I just have to make sure that the interval is sitting within here. Okay, so take the length. What's the length of these intervals? Well, they're halving each time. So we started off with AB, and we're halving each time. So length of AB, written like lambda. Lambda is the symbol used to denote the length function, is b minus a. The length of the interval in is equal to b minus a over 2n. Okay, so all I need to make sure is that b minus a over 2n is less than the minimum of these. So there's some number though, that is some number. So let's call the minimum of these, let q equal the minimum of these two values in a set. There. Then we just let it equal less than q. Therefore, swap this over. B minus a over q needs to be less than 2 over n. So n just needs to be greater than log to base 2 of b minus a over q. Right, and remember n also needs to be a natural number. So just take b minus a, find q, whatever it is, which you can do. You can calculate this number, b minus a over q, then take log to base 2 of it. You probably won't get a natural number, you'll probably get some real number. Just take the first natural number that's bigger than it, or just take any natural number that's bigger than it. You're in with a chance. I guarantee you then that interval in will have length less than the minimum of these two, and therefore interval in will be contained within that open set. So I'll just write that up and then we've completed the proof. So in, where n is greater than log to base 2 of b minus a over q, will be contained within the open interval containing u1, u2, which means that in is contained within ux, which means in has a finite subcover. Contradiction, because we constructed it so that it didn't. Contradiction, because we constructed it so that it didn't. Contradiction, because we constructed it so that it didn't. Therefore, this implies that the interval AB, the closed bounded interval AB, which is a subset of the real line, is compact, i.e. that any open cover has a finite subcover.